Just a moment. Okay. So, hi everyone, and I'm Eduardo Martins, and today my talk is going to be about the NAS Pro benchmarks in Rust. I'm a master student at Pontifical Catholic University of Rio Grande do Sul, so in Brazil. And I'm a member of the parallel application modeling group here, and we like to work with HPC stuff. So we have research lines in string processing, parallel frameworks, interfaces, and abstractions, compilers, GPU, and also benchmarks. So the NAS parallel benchmarks, or NPB, is a suite of benchmarks applications that were developed by NASA in the 90s. So the idea is that they provide this benchmark to comparing the performance of highly parallel supercomputers. And it contains 8 different benchmarks that are derived from computational fluid dynamics applications. So here I have a short name from them here and each of them are intended to enforces different aspects on the hardware of the target machine. So for instance, CG application is a um, CG applications enforces the aspects like communication overheads and also memory locality. And we have a different application like EP, which don't have any communication overhead and is intended to test floating point operations. So each of them, it's very specific and has its own characteristics. Uh, Also, they have different configurable workload size, which we call classes. And in this work, we are going to use class C as it's more suitable for shared memory environments, and it's the most used for this end in the literature. The NAS Pro benchmarks was originally available in Fortran, in sequential versions, and also with parallel versions for shared memory with OpenP, and also for distributed environments with MPI. And since then, several releases were proposed by the community. So today we have versions for CPP, Java, also Python, and for different architectures like GPUs. So today we have parallel hardware everywhere, and we need to be able to evaluate the different frameworks for expressing parallelism in terms of performance and expressiveness. So we also wanted to include Rust in such evaluations. So we observed this lack of benchmarks that represents arithmetic tasks and scientific applications in Rust, and we decided to provide a Rust version of the NPB. So in that way that other developers that are developing frameworks for parallels, they can test a Rust solution and compare with other Rust frameworks, or even in a multi-language scenario, they can use the different versions of NPB to do so. And also, since we are developing the NPB Rust, we also wanted to include a Rust performance evaluation. So regarding the implementation of these applications, we use the C++ code as the baselines for the porting process. And we have two main design principles that we followed. That was basically retaining the algorithmic structure and following the original sequence of operations in a way that we can have a fair comparison at the end. And also we tried our best to embody the best practical of the Rust language and programming in a idiomatic Rust code. And after our porting process, we ran a profiler to understand which were the bottleneck in each application. And if you find out that the application was struggling because of any of Rust safe checks, we also wanted to provide an unsafe version of the application. So this was the case for IS, MG, and FT. So for those one, we provide an entirely safe version, and also with some a version with some unsafe optimizations. So for our experiments, we tested on the Intel Xeon machine with 20 cores and 40 with hyperthreading enabled. And we use as compiler Rust, of course, 1.81, Clang 10, and G-Fortran 9.4. So the main question that guided us through our experiments was, does Rust language provide sufficient performance and expressions for the NPB algorithms? And here we can see the results of the sequential version. So here we have each applications in the x-axis, and in the y-axis we have the execution time in the log scale. So we can see that Rust in red here indeed performed very well and achieved a performance of 5.6% faster than C++ and was 1.2% slower than Fortran. And also we can visualize here our performance that we achieved using unsafe. Here in the MG is an edge case because this application has a lot of irregular memory access. So this is why we have this big difference right here. And for the parallel tests, we used Ryan as parallel framework to compare it against OpenP in both C++ and Fortran. So here we have the results for 3 of the 8 applications. In the x-axis here, we can see the degree of parallelism, and again here in the y-axis, the execution time in the log scale. So in AP, that is the smaller application in terms of parallelism. Our frameworks were able to scale very well, but Rayon still outperformed the OpenP because of its dynamic work stealing scheduler that performs better when achieves the hyperthreading point at 20 cores. And when we go to a more heavier application, such as BT, this becomes more evident, but still when it reaches 40 threads, the OpenP with Fortran were able to have the best speed up. And lastly, I bring another edge case, again with MEG, where this application that is known for stop scaling with a lower number of threads. So you can see that from 6 to 8 threads, it starts to go more horizontally. This happens because this application reaches a small granularity very fast, and the dynamic scheduler in this case causes some overheads. And so we provided the NPB-Rust, so other developers can test the Rust solutions, and we tested again C++ and Fortran, and it achieves reliable results. Indeed, Rust outperformed C++, but was a little slower than Fortran. And for the parallel application, parallel versions, the OpenP outperforms Rayon. So we are currently testing these benchmarks in different architectures and comparing with other frameworks for parallelism, such as 1TBB, which also has the dynamic scheduler. And so if you are interested to understand more about this project, you can check our GitHub here with this QR code, and there you can find also a link to our preprint paper. So that's all for my presentation. Thank you very much.
Thank you very much, Eduardo. We have some questions in the chat. So one of them says, are the implementations good to study how to write high performance algorithms, or are there any benchmark considerations, abstractions that make it less applicable to general problems?
Yeah, if you're interested to learn about hard performance, these applications, it's a good way to learn about it, but they are very advanced. So maybe we can try with smaller applications, because NPB applications on average, they are like 200 lines of code. So I don't know if they are good for learning that, but I'm sure that they are very good to learn about high performance.
Okay. And there's a second one. Maybe it's worth asking now. It says, could you go in more detail on the C++ Fortran execution time jump from 20 to 22 threads? Why Rayon doesn't have it?
Okay, yeah, sure. So let me go back here. So for example, here, OpenP uses a static scheduler. So basically, when it reaches the hyperthreading point, it will gives for one process double the work. But as we know, one core doesn't have the double the capacity to deal with this. So, and the application will be bounded for the slower threads. So when we hit 21 threads, all the other process will need to wait for one thread that has the double the work to do. And as Rayon implements the work stealing, the Rayon will steal this work and uses as dynamic scaler. So when it reaches more threads here, with the OpenP, we'll be able to get more evenly again with the scheduler. Sorry, I think I don't know if it's clear enough, but
It's okay. I'm gonna ask one last question because someone is insisting that it should be answered. I didn't see it because it had been answered before, or like had been replied in the Q&A. But it says C++ performance can be affected by different compilers. Which ones were used to get these results?
yeah, sure. We used Clang in this case because of the LLVM, and we didn't compare with other compilers, but you can find results that compares these different compilers if you look for the paper of the NPB CPP version. So in this paper, they did some comparison between different compilers, but in this work, we opted for the Clang because of the LLVM.